Today's lecture is on inputting, editing in GIS. Inputting involves scanning and digitization, and then creation of a GIS layer. And then editing is basically whatever you input. So basically you correct the errors, remove the errors, and then make the final layers. So basically what we are talking about is scanning, digitization, removing errors and creating a layer, final topologically ready layer. So that is what we will be discussing in today's lecture. So what is digitization? So you might be hearing many things nowadays, digital India, digital world, and then paperless office, e-governance. So there are many things coming to your mind. In our context, so digitizing means whatever is there in an analog form. So either it is in a paper, or it is in a map, or you have in a tabular form data converting into in a computer digital form. So that's why digitization means converting analog data into a digital data. Basically, it is digitizing means what? First of all, you have to capture that. How do you capture that? That we do it through scanning. Capture that existing data, existing maps. So number of digitizing techniques are exists. So we will be discussing in detail all those things. And then scanning can also be digitizing. So as I mentioned earlier, so once you scan it, it is also called a digitization. See, nowadays you are all well versed with smartphones. See, if you talk about maybe 10 years or 15 years back, so no smartphones. It used to be only the scanners. So nowadays, even using your smartphone, so you can capture the maps. Even some of the smartphones comes with what is that continuous mode photography, where you put your camera and swap it to the area. So then it takes the whole area and creates an image. So that is also one way of scanning, you can say. Or you rotate your eyes from one location to other location to capture that what is there in front of you, which is, so that is also called scanning. So in case of our case in a GIS, we have many different type of scanners are there. We can have everything you scan at a time, or you can scan part by part and then convert it. So like that we do it. So scanning and digitizing are important components as part of a GIS database creation. So if you see this next document, what you say, there is a document is there, which is called a document. And then that what you can do is either you directly take into the scanner, fix it to the scanner, or you can directly take it to the digitizing board. So what I'm telling is, this is digitizing board is a you can say it's a mechanical device, and then basically the electronic mesh which grid is there inside that, and then it looks like, suppose some of your engineers, you also do a lot of engineering drawing as part of mechanical engineering, civil engineering. So everybody does also, it is drawing also is common for many of the engineers. So your the digitizing tablet, what I am mentioning is, it is also similar like your drawing board, but there these are drawing board, the size varies. So if it can be A3 size, or it can be A0 size, or A1 size. So if you go to the internet and then try to find out each size having a certain measurements. So normally the maximum size what we call is A0 size, that's 36 inches, 36 into 2.54 centimeters. So it comes around 900 millimeters or 90 centimeters the width, and then it can be length according to 1 meter or so. So these are all the A0 size maps. So you can put those maps onto your digitizing board, and then once you put this document onto the digitizing board, so what you can do is you can directly use the mouse. Earlier days there used to be a 12 button mouse, 16 button mouse and 4 button mouse. So like that these mouses used to be there. It is they we basically did not call them as a mouse. This is a cursor device. So there is a cursor here is there in this one, transparent this thing. On that you have mouses, and then electronic wire is connected to the digitizing board. Whatever you keep on this digitizing board and then press the button, you start entering it. So automatically it will add into the your computer. Other option is you scan through scanner. It can be a drum type, flat type. There are different type of scanners are there. So I will come to that again. So once you scan it, so it becomes a JPEG image or TIFF image. So that image you load into your screen. On screen means your monitor. So once you load onto the monitor, and then that you can further use it for digitization process. So here if you see this, the document, whatever you put on that, so it is basically digitized manually. So that digitization, it creates that basically line feature. In this case it is a river, these things shown as a line, and then we have a agriculture or vegetation features shown as a polygons. So this basically converted into a your vector format. So it is shown in the form of a two-dimensional vector where each point having a x1, y coordinates. Another process is that once you scan it, so then you put it on screen, and then you see that it is converted into raster pixels. So these pixels we have created a raster, and then from this you can also vectorize as it is shown in here, or directly can go to the spatial database. So that means whatever is there on this, basically when you scan it, we will also do after rectification and assign the values. Each pixel you assign a value, and then before assigning value it's only digital number. Once you assign value, it will digital numbers are converted into a particular feature with their attribute. Then it goes to spatial database, and then that database used for further analysis and operations. So coming back to this thing, digitizers, as I mentioned. So if you are not seen in our lifetime, you are all young people. So these digitizers are not there now in the market, or it is at the user place. So we used to have this type of digitizers at IERS. So there is a big digitizer, A0 size. This is also a big digitizer. You fix a map onto this and start digitizing it. So this is a cursor mouse which is placed, and then start digitizing, and then this is the place 4 button mouse. This is a A3 size digitizer. If you add two papers together adjacency, A4 size, so that becomes a A3 size. So there is a on the board there is also called a transparent sheet is there. You can lift the transparent sheet and then put your paper below that and then fix it. So then you can start digitizing it. So it is you say 1990, 95, that is the time where we started using this. By 2000 or so, so it is slowly change it to the scanner and then vectorization. So basically scanner technology which has developed later, but digitizer board came first. So that's why people started using a digitizing board initially. When you talk about digitization, it can be on-screen digitization. So then you can do two ways. One is a manual method, another is a semi-automatic method. In case of manual, each point, line and area you digitize manually using your cursor mouse and then once it is digitized, so you use for further editing and then creation of the layers. Another is semi-automatic. So when you talk about automatic means, suppose I have a map is there is a line on the map. Instead of manually putting your cursor all along this, so line, what I will do is I will ask the computer to vectorize. I ask the GIS layer to vectorize. So then whatever the line is there on that, it automatically vectorizes. So that means it creates the coordinates for each point, and then it also creates the nodes in between that, and then line is drawn. So that means whatever is image is there, it again convert into a vector layer. So this vector layer is what happens is you'll have the line segment as well as the coordinates for that line segment. It is basically what I say is, if you convert everything automatically without a manual intervention, so that what we call is a automatic vectorization. So that's why when you say digitization or vectorization, it is a manual method, either manual, either semi-automatic or automatic. In case of automatic, as I mentioned, you scan it and ask the computer to convert, it will convert the whole information. Another thing is, this is a manual plus automatic is called a semi-automatic. So what we will do is, we will start digitizing, take a point and then start asking your computer, a GIS software, to follow a particular line. So while following a particular line, if there is no break and then there is no other line is crossing with this, so computer, it goes very fast, taking one point, another point, unless it faces any junction in between. So then it will draw that. Suppose if the bigger line has to be drawn, so there is no intervention or there is no crossing of line, so it does very fast. So manual method anyhow, it takes a long process. In case of semi-automatic, it is very fast. So coming back to this on-screen versus manual digitization. You yourself visualize when you say digitization, topographic map. So that topographic map, if you wanted to digitize, follow many features. So what will happen is you require a lot of time. So that's why, and then your digitizing board, you keep these maps, and then if somebody disrupts, so then again restring into exactly this will be difficult. So that's why in case of a manual method, once you keep it under this thing, digitizing board, if somebody disrupts, so then it creates a problem for us. So that is our first disadvantage. So that's why it is always better to the scan and then bring it to your computer monitor. So the same you can do many times. Suppose you stop somewhere in between. So then you can take up again wherever you stopped, because it is already georeferenced, and then again reloading is not there on the digitizing tablet. It is only to the monitor you are doing that. So it becomes easier and faster. And another is, it is also more accurate. Suppose you wanted to follow exactly at the middle of the line, you can zoom that line into very thick and try to follow that line. So with the zooming facility is very easy and comfortable, and then it will be also more accurate. If you do it in a on-screen digitization compared to manual. See, I am explaining this thing, but see, manual is now almost outdated because nobody is using it. So this is only to give you an understanding how we used to do in earlier occasions. So faster is you do semi-automatic digitizing and editing the same time. So semi-automatic, what it is said is digitizing and editing at the same time, means you are removing the errors also. So another important thing in case of on-screen and manual is same work can be shared. So if you have manual digitization using the digitizing tablet, again it is only for theoretical explanation, but otherwise now we are not using a manual digitization. Same work can be shared. Same, if you scan some map, give it to 10 people, you ask all 10 different people to digitize 10 different themes. So that means water bodies or what I say is land use land cover map you wanted to extract, or road line you give to somebody, point information, post offices or something, hospitals you give it to somebody. So like that it can be done. In this updating, that is a lot of advantages. Updating is easy. Geometrically corrected satellite image, scanned aerial photographs can be also overlaid with the old vector data. So it is, suppose you have some digitization is going on, you wanted to check it with the actual image, whether we are doing proper vectorization or not, if it is a road line. So you can also check exactly it is falling on that. If it is not falling, maybe there is proper registration is not done, etc. Another is map registration. There is very important component. You put it your map onto the digitizing tablet, where you have inside there a lot of wires. So those wires basically transmit a signal wherever you click on the map into your computer, and then as if it is recording the your map. So like that it can be done. So another, that's why when you start digitization, first process is map registration or georeferencing of the image. So your board coordinates will be converted into a world coordinate system with a registration process. And then when you put it into the digitizing tablet, it's having its own coordinate, but those coordinates again we can convert into a world coordinate system, convert into a according to the location you are giving a what are the coordinates for that each point. So converting basically from the digitizing tablet value into a map coordinate system. So once you have digitized, then it is possibility of that getting some errors. So those errors will be in the form of overshoots, undershoots, as a sliver here, or a duplicate lines. When it is digitized, if computer notices this thing, there is a dangling node. So it show in the form of a red color, showing a different color, so that you can see visually and then go to that place, each place, and then start rectifying those problems. So these are the errors. So in a GIS, these errors can be removed manually. So you have to do for each location there. So before what in a GIS we also called a node and then vertex. So node is the point from where you start, and then vertex is the line what you create. So suppose if you take in this example, so there are different lines are there, and then once here 3 lines are created with a certain node, another line is created, but that is not matching with that other node which is supposed to be. So there is a gap. So these type of thing when you do it, so you can also set the snap tolerance. So that means if you draw a line and you bring your cursor to that line and to create another line, what you have to do is you have to split that line and then create a node. Suppose if you don't split that line and you start drawing that line exactly from that point where it has ended. So then when you zoom it, we will know that this point is not added to that earlier point. That means it is not connected to that earlier point. So there may be, it may be overshoot or undershoot. So if you keep some snap tolerance, some buffering distance between the existing node and the new node, if you bring exactly to the near to that and within that snap tolerance, so then it will join that line with other line. So it is basically does the distance calculation, how much distance you have given as a snap tolerance. If it is within that limit, so then it automatically try to join with that earlier point or earlier line which is having one node. So then this go and joins there. So this happens as a joining process. So the snap tolerance, basically as a default you'll have a small snapping tolerance. You can also create your own snapping tolerances. So it will help you to complete the process of creating of a layer, because if you have some nodes which are not joined, so later on if you wanted to run some network analysis, so it becomes very difficult, because your line, if you wanted to make it optimum route, the going from one place to another place, if the line is not joining, it will be dangling somewhere. So your line is continuously not connected. So then it will not work for your further analysis if you are not completed this process. So identifying and interpreting the errors. Suppose if you see this, there are pseudo nodes and label points, dangling nodes and missing labels. So as it was already mentioned to you, we have overshoots, undershoots, and then when you create a layer, so you'll also give some label. So you say agriculture or something. So that will have some value for that. So that label, if it is not given, suppose in this case, so there is a missing label in this. So that means 217 and here is nothing. So that becomes as a missing label. Similarly, you have a pseudo nodes. You have created a pseudo node, and then you have a label points. Suppose each label point, if you are given, it is also symbol is given as a plus sign, and then dangling node which is not joining with other polygon, other line. So these are all called dangling nodes. It can be overshoot or it can be undershoot. So normally people suggest that you always do it overshoot, so that wherever it crosses that line you wanted, so there it also creates a nodes, and remaining which is coming beyond that point, it will remove it. So, and another important thing is when you wanted to have a point digitization, you can have a digitization two modes. So if you take a cursor and put it at one point and then click, and then again you move it to another point and then click. So that means between 2 points we have clicked twice. One is creating of a nodes, and then you have taken your mouse and put it at another place. Suppose if there is a road is there, so if it is going straight line, what you do is take from one point and then go as long as it goes straight. So then it creates a line between these two without digitizing in between. So that means it will consider that from first point to second point, this is the line direction it is taking place. Similarly, second, third and fourth, like that you add. So that means each point wherever you wanted to conform to your GIS software. So then automatically your line is created with nodes at each place. So like this line is created. Point mode, this is called a point mode digitization. So the control is with the person who is digitizing it. Suppose I click at one point, so then the node is created, and then you take it and then vertex is created. Like that it happens. So that means every time I click, then only the line is created. The vector line is created, or polygon is created, or a point is created. And then another is, suppose I know that I am digitizing according to that layer what I am having. So what you can do is you can take the mouse all along that line with that cursor whatever is there on that. So the system takes care of the digitization of the whole process. So, but only thing is you have to move at certain pace, so that in each second some number of points are created. So if you do very slow, so then your data capacity increases tremendously. Even there is a line, straight line, so I do slowly from that line. For each second, suppose some nodes are created. Some for 10 seconds or each second it is created. If you draw that line and then if it takes 10 seconds, so it will also create 10 nodes in between that. So that means data storage will be increasing that way. But when you move the cursor, we need not press any button. So first button you have to press, and then wherever you want to stop, you have to press it again. So but in between it creates the whole line. So in case of the stream mode digitization, what is happening is there is a line, it is there. So the thin line. So and then so many you see so many nodes have been created. So those nodes basically are extra. So those things also you can avoid, and then keeping some tolerance limit between the line, so that if it suppose I draw a line with a certain going up and down, so if it goes beyond that width of that this thing along that line, what will happen is if going beyond that, then only it changes the direction. Suppose if it is within the line, so if it is going line is drawn, it will draw a straight line. So then you have to go to other points. So like that, it creates the tunnel and see wherever the points are there within the tunnel. So that there is a center line is drawn. So this is the center line, point 1 here, point 2, and then there are 4 points in between, but we are taking the point next to that after 4 points. So that means when the cursor is moved along with that line, but it creates that thicker line is a straight line. So it uses that tunneling tolerance level, and then it reduces the unnecessary nodes when it is creating the line. So this is a stream mode digitization. One is a point mode digitization, which is completely manual. Another is stream mode digitization. It is also manual, but you need not kick, you need not press the cursor for each point, but you just follow that line seriously. So then you can create a more accurate line with this stream mode of digitization. So we just discussed what is digitization and the different modes of digitization, that is point mode, and then what I say is stream mode. So let us come back to the scanning. So when you scan, basically you have camera based scanning. Another is you have a camera is basically uses the lens. Another is what you do is a CCD, charge coupled devices. So these charge coupled devices, there will be many devices in the all along that scanning. So each CCD will be used to scan certain area. So that becomes the resolution of that map for the scanning. So in this, what we are using is computer using a CCD based device called a scanner. See, as I mentioned earlier, nowadays you capture with your camera, and then there you talk about the resolution. So what is that? 9 megapixels, 20 megapixels. In case of iPhone, they talk about 40 megapixels. So that means the captured image will be having many pixels. So the more the number of pixels, the smaller is the size of the size of the dot what you are capturing. So that means there are many number of pixels you are capturing. So there is minus part also you can scan. So that means the higher the resolution, what you say, your camera, so you can capture the smallest size. So that's why you can high resolution, very high resolution. When you come, your length of the focal length increases, so it goes to very narrow. You can say if you put a tele lens and then try to see, then you can see very finer details of the smaller areas. So that gives the higher resolution. Similarly, scanners also, you have more CCDs are arranged, so then you'll have a better scanning can be done. So, and then scanned map is in the form of image and raster. Another thing, important thing is when you say technical information, talking about a camera, it is basically megapixels. If you have higher megapixel, it is high quality. Similarly, when you talk about a scanner, it is a CCD rays, and then we represent in the form of a DPI, dots per inch. If in a inch, if you have 100 dots, we say 100 dots per inch. So the resolution is called 100 dpi. If you in the same inch, if you have 600 dots, we say 600 dpi. So the higher the number, so better is the resolution. So a few days back, I went to some steel shop. In that, they are talking differently. So thickness of the metal, if you are measuring, so they say gauge 20 and then gauge 40. So their gauge 40 means in that in a inch, if you talk about, so that 40 divisions can be done. So that means the thickness there it is reducing. If it is 20 divisions, the thickness is higher. So there the lesser the number, the better is the thickness and higher the strength of that steel almara what we say. But here it is the higher the number we have, the better is the resolution. We have to digitize this image or raster in order to basically whatever you scan it or this thing, finally it is converted into a TIFF or JPEG image. So that in case of a GIS, you further georeference it and then start digitizing it. So then once you start digitizing, it will be converted to your vector map. So these are the different type of scanners. You have a flatbed scanners. Flatbed means you have the scanning device which is kept on the table, and then there is a light device is there, and then below that you have a glass is there. Suppose if you have paper to scan, so if you want to scan the text, basically you put it like this, and then the light is coming below that, and then it is scanning. So these are all test based scanners. So these are all called OCRs. So I don't know how many of you heard of it. Optical character recognitions. So once if you put the paper with the complete text, so there is a software. Once it is scans, it also recognizes those words. Suppose there is a word is there, automatically it will convert into a word. It will be text file basically. So these are all character based recognition scanners. Normally what we use A4 size. Earlier the OCR also people used to come. You buy a scanner and then we'll also give OCR software. So that if you have old files with so many text is there, automatically instead of retyping, you can convert into the text. In case of a GIS, we are more concerned with your images, your maps, your lines, all these things we are concerned with the maps. So that's why A4 size, if you talk about that, our maps are not in the smaller size. So they are the bigger. So either you should go for A3 size, the next scanner is A3 size, or still the bigger scanner is A4 size is here. You can go with this or you go, particularly for a GIS purposes. So this is more of a text based, or you can keep some object for children if you wanted to show something and then scan it. So that way it can be used. These are the different type of scanners. And then the scanning process, how it happens is, so once you have a drum scanner or flatbed scanner, so you have a fixing the image onto this drum type, and then there is a optical splicing. So that means you are taking that image, the information, converting based on, maybe I can do it based on the color, based on the grayscale. So I can extract the information and put it to the computer. Suppose if I take a topographic map and then I wanted to scan it, if you scan it at a one stroke, you'll get a color image. Another thing is you can also scan it, extracting the particular type of the color. So that means here itself directly we are converting the information what you wanted. Suppose if the contours are there in a gray scale or something color, so that if you are trying to extract, so then you are trying to eliminate other information, extract what information is required. So then the vectorization process is very fast. Otherwise, you scan and then you try to extract each one by one again. That is also more of a manual process. It involves a lot of time for the converting of that. Another scanning method is, suppose you have a paper is there, so you eliminate the proposed paper is there, you eliminate the paper, eliminate means, this is something like illumination means you put the light and then put in light there and then you put a sensor there. There is a light is coming here and then paper and then sensor. So sensor captures that information and stores. Another is we have a transparent film and then one side is light source is there, other side is the sensor is there, and then you capture it. It is something like a, in movies we used to have films earlier, so that films continuously runs. One side the film is going on, one side you send the light, and then with that light and that picture image will be shown on the screen. So here also we have a transparent sheet, other side will be the sensor, you capture that information and then you store that one. Coming back to digitization, once you scan the image, what you have to do is, suppose this is something like a aeroplane or plus sign here. So this is that what you scanned here, and then after the scanning, I wanted to while scanning itself, we scanned with a certain resolution. My resolution is 0.05 millimeters. The size of the cell is 0.05 by 0.05 point. Whatever is there on the map, so that means 1/28th of an mm. So if there is a, you draw a dot, square dot, and then if you, that dot is 1 millimeter, so then when you scan that dot, I am dividing that 1 millimeter into 20 parts. So 20 by 20, that means 400 pixels I am creating for that within 1 millimeter. So that is your resolution. So the scanning resolution is 0.05 millimeter. So like that you scan it, and then you see there is a box is kept here. So what it is showing is, so this is the whole image which is captured. See, in scanning it doesn't recognize whether there are white spots are there or it is a dark spots. It according to the color, so then it captures as image. So suppose if it is completely white, it is stored as a 250. If you see, I don't know how far you are able to see from your side. It is shown in a green color, 240, 249, 220. So this, even the white spot is there, but there is a small line is coming. So and then if you see, somewhere is 249, 253, 252. So wherever the white is there, so it shows it a highest what is that reflectance coming from that. So it will store as the highest value. But wherever the dark patch is there, the response is coming very less. So it can be 14, 35, 8. So something like that it is giving the values. And then and then those values are shown here like a 30, 15, 15, 10. So like this basically it is converted into a your square grid showing the values. So and then once this is the way where you get a final image, JPEG image or TIFF image having these values. So what resolution we have scanned, it is in millimeter, 0.05 millimeters. If you wanted to show in a micron, so 1 millimeter is equal to 10 to the power of 3 micron. So that's why 0.05 and then multiplied by 10 to the power of 3, that is 1000. So it becomes a 50 micrometers. And the same thing if you wanted to show in dots per inch. As I mentioned earlier, in an inch, suppose if it is 0.05 millimeter, in a particular inch, how many dots are coming? So for 1 millimeter, you have 20 dots. It is 1 inch is equivalent to 2.54 centimeters. It is also equivalent to 25.4 millimeters. So you multiply 25.4 into each millimeter is 20 dots. So that means multiplied by 20, you will get 508 dots. So what is the basic thing you should consider when you do a scanning? You should not do scanning arbitrarily. I'll do it highest level so that I'll get a good resolution. Then at the same time, it is also difficult for the computer or your storage devices. You should have a very high storage space is required. And what way, how much is my minimum scanning resolution? That you should understand and then do that. So the general principle is for manual or on-screen digitization, if it is there 200 to 300 dpi, that is quite enough. But if it is automatic and semi-automatic, we at least have 1/3 of the thinnest line. So that means if the line is there, so that line you should divide it into 3 parts. So each part basically three dots, so that if you are doing automatic vectorization, you should follow the middle line. Either it can be three dots or 5 dots, but 3 dots are enough. So line should be at least 3 pixel width. A resolution of 300 and 600 dpi is the most sufficient in most cases. In case of photogrammetry, you use basically photogrammetry is flying through aeroplanes, so they are flying at the low height, so automatically their resolutions will be very high. So to keep that resolution at which they are capturing, so that's a photogrammetric. If you use photographs, so that can be scanned with very high resolution, so 800 to 2400 dpi. In hard copy output, 2 times the resolution of the printer, that is enough. So going further, so to give you a further clarification how that 0.05 mm is converted into 508 dpi, and then what is these dpi, how to represent in the unit of microns. So let us see. As I mentioned, 0.05 mm is equal to 50 micron or 508 dots per inch. So let us see 508 dots are scanned in 1 inch. So that means 508 dots equivalent to 1 inch. So the same 508 dots equivalent to 2.54 centimeter. Hence, size of one dot, suppose if it is 588 dots in 1 inch, now what will be the size of one dot? So this 502.54 is the 1 inch. So that you divide it by 508. So then you will get a 1 dot, size of 1 dot. So 2.54 centimeters divided by 508. It is equivalent to 0.005 centimeters. So that is still equivalent to 0.05 mm. So basically 10 millimeter equivalent to 1 centimeter. So they basically 1 centimeter, then you multiply with 10 mm. So then 10 will be still reduced. It will become 0.05 millimeter. And then as I mentioned earlier, 1 mm is equivalent to 1000 microns. So 0.05 millimeters, you multiply it by the 1000, it becomes 1000 micron. To give further understanding, 1 micron is equal to 10 to the power of minus 6 meters. So you convert it into centimeter, it turns power of 4, again multiplied by 1 meter is equal to 100 centimeters, multiplied by 100, 10 to the power of minus 4, and then 1 centimeter is equal to 10 millimeter, so it becomes 10 to the power of minus 3 millimeters. So therefore 1 mm is equal to 1000 microns. So this will give the understanding for you. So there is here one image is there. So let us work out this image. Suppose I wanted to print. I wanted to print this image on a paper. This is an image in the digital form, that is having 1000 by 1000 pixels. I wanted to print it in a 10 centimeter by 10 centimeter size of the paper. So my question is, what DPI the image was printed on the paper? So what is the size of one dot on the paper? So that means, as I mentioned earlier, size of one dot is 0.05 millimeters, but that we converted into microns. 0.05 multiplied with 1000, so it became 50 microns. So similarly, once you know that size of each dot, so then you convert into microns. First is, what is the DPI? The image was printed on the paper. At what DPI? So at what, how many dots will be there when it is printed in 1 inch? Now what is the size of one dot? So that also you have to tell in micron. So let us see whether you understand what I mentioned. So just think of it, and then we'll just 2 minutes I'll give. It's not 5 minutes because today we started late. So just take 2 minutes and then work out, and then you send your answers. Don't take it from the image what I displayed, but you should think your own mind, and then try to find what is the DPI, and then each dot is what is the size. Tell it is in microns. So it is basically what is the DPI? What we mentioned is it is 254 DPI, and then each dot will be 100 microns. So that is the final answer. So the output paper will contain 1000 pixels, and then that we are printing in 10 centimeters. Suppose in 1 centimeter you wanted to find out how many pixels will come. So in that, suppose 10 centimeter 1000 means in 1 centimeter you have 100 pixels or 100 dots. So 1 centimeter is equal to 100 dots. But what we wanted is, we wanted per inch. 2.54 centimeters, how many dots will be there? So 2.54 per centimeter we have taken. 2.54 centimeters into, for each centimeter is equal to 100. So it becomes 254 dots. Or you can also mention that 254 dots per inch. So, and then if you wanted to work out each dot, so size of pixel or dot is equal to 0.01 centimeters. You see, if you say 1 centimeter is equal to 100 dots, you just reverse it. So 1 dot is equal to 1 centimeter divided by 100. So it becomes, so 0.01 centimeters. So that is also equivalent to 0.01 is equivalent to 0.1, because each centimeter having a 10 millimeters. So then it becomes 0.1 millimeter. So then you know that each millimeter how many microns? 0.1 multiplied by the 1000, you will get 100 microns. That is the solution for this. And then when you scan it, another important thing is either for what purpose you are doing scanning. Suppose if you wanted to convert if you wanted to convert the map into a digital format or a vector format, so even you can think of even 1-bit scanning. Suppose you say that what is present or not present, present is 1 and not present is 0. So then basically that again you can convert into your vector. So whatever the line is coming, and then you vectorize it. So then once you vectorize, so then you assign the other values, attributes to that. So sometimes 1-bit scanning also works for particular applications. So in case of contours here, it is enough. But another is 8-bit gray mode scanning. Suppose if you talk about satellite data, we normally represent in 256 colors. So to represent 250 colors, you have to have 8-bit information. So either it can be from 0 or it can be 255. So and then basically black and white images, if you wanted to vectorize, basically you first scan it in 8-bit mode, and that 8-bit mode later on you can also use it for converting into information automatically, or you can otherwise you can use for manual purposes also. And then scanning output is, the scanned output is only digital copy. See, basically whatever you scan it, digital copy of the source document in raster cell values. So there you have to understand. Basically, you are converting into a raster image. Data are not structured into classified and coded objects. So they are basically the pixel values. It is something like a satellite data. Raw values will be there in a digital numbers. The data actually, when you wanted to use it for a GIS, so basically they have to be vectorized. So further editing has to be done. You have to assign values. That means attributes have to be given. So then your information right away can go to the as a GIS layer. As I mentioned earlier, automatic vectorization process is also involves. I said what is automatic vectorization. So you give to the computer, it vectorizes then the raster information into the vector. So if you talk about automatic vectorization, there are two steps. Step one is skeletonization. So that means you uh, thin the line. Suppose if there are one line is there, so there are the line consisting of a thick line, and then that line, if you put it into the computer, it can also put into many pixels. The cross pixels may be 10 pixels, 5 pixels, 3 pixels, etc. So that you have to vectorize, you have to skeletonize, reduce the thickness as much as possible, and then come to the center line. So drawing a center line is also called a skeletonization. And then once you skeletonize it, and then you are also assigning attributes. Suppose if there are, you scan an image, there are many lines are there. One is a big highway, like as I mentioned, Delhi to Agra. And then if you also talk about the national highway, it is also having a good width. But if you go to the state highways and other things, so it will be having a different. So then when you create a GIS layer, you also assign the attributes according to the type of road it is. You have to say that it's a Grand Trunk road, or it is a national highway, it is a state highway. So that you have to do, that is called a feature forming. So that these are the two steps when you convert from the raster to vector. See, if you see this, the lines of a map, this is the original map, and another is then from this what we do is you scan that. Once you have that, you scan that lines, and then once you scan that line, so then the pixels are found. If you see this, so there are 4 pixels are formed here, so there are 3 pixels are formed here, 3 here, so here somewhere 4 and somewhere 5 or 4. So this basically it is a whole raster image. So that what we do is we do the skeletonization process. Remove all pixels that make the line wider than 1 pixel. So that means whatever wider than 1 pixel, everything is removed, and then your vectorized line is created. So carefully see this. Our original image is like this, straight line. But after skeletonization process, you have a line here, but instead of straight away joining, it is going like this and coming back. And then there is also unnecessary one more spike has come. This is something like a overshoot. And then this line also is not joined. And then this is also not straight line joining. And this of 2 bends, there are many bends are there in this. 1, 2, 3. So like that it happens. So that means the original to the final vectorized line. So this is problems. You can also say that problems if you do automatic vectorization. So this is the original line what we have, and then you what you do is that you scan it. So it is creating a scanned output with number of pixels for each line. And then, as I mentioned, it is skeletonization process. When you do skeletonization, we will keep only one line process, and then this is the skeletonized output, and then this is the vector line what is forming with in the skeletonization process. So if you overlay original line feature and then vector line skeletonization one, if you see that there are a lot of matching is happening at many places. but at some places still there are some errors. So blue line is the original line, vectorized line is red line. In this case, so this all happened because of instead of the width is instead of 3 pixels width, it has taken a 4 pixels width. So it is also not possible always. I say that I want to do only 3. So that is possible if all the lines are the same thickness. So probably this line thickness is higher. So that's why created 4 dots, and then there is no center pixel line, because that you require either 3 or 5 or 7, so that it automatically draws the center line. If it is a 4 pixels, there is obviously there will be shift. So this is the difference between the original this thing. Then you see that vectorization editing, how it is taking place. So this is the scanned image what you have, and then dots it is created is a noise here. And then as I mentioned there earlier also, when the line is like this, it is joining. In the vectorization process, instead of straight line, it is taking as a diagonal one and joining. So there is a gap in between here. So because of the not having a proper line creation, maybe there are spikes are created. The computer is not understand. Suppose if you thick line is drawn or thin line is drawn, or while drawing it going out of that, and then also create another line on that, but actually it is not that on the ground. So this thing also it does vectorization process. So in joining also, that instead of exactly joining cross, so there is a gap in between that, and then this line what is showing, instead of exactly joining corner, it is also created a bend here. So this you have to apply the processing and remove all the errors. So then what you are doing is you are creating the almost equivalent to original line as a vector created lines. This is the process what it is done. So once it is done, vectorization is done after a vector editing. So the lines have been created, but there is no attribute here still. So what you have to do is this one, splitting the lines to form the line segments and nodes. What you are doing is, the lines are there, but it is created as a line. So but it has not created any node. So without the node I mentioned there, suppose you wanted to continue and then network analysis, so your nodes also have to be created. Joining line segment to form the polygons and features. So if it is a polygon is there, you have to have all these line segments have to be joined together, but with the starting point and end point should be the same. And then whatever you created, there should be a feature coding. So you see there is a red line which is the main road here, and then there are nodes, that is junctions. But this is a different type of highway here, main highway. So this is another highway road with a node created here and then created. So another I wanted to ask is, suppose we do some scanning. So in that scanning, and then we wanted to convert into vector files. So then the point is, which type of vectorization process we should use? Shall we use always automatic so that it becomes faster, or use some semi-automatic and manual? There is no thumb rule, but normally seeing the type of features, you can decide. Suppose if you talk about these green lines, so they are all contour lines, and then it is showing as if the lines are joined here. But if you zoom that certain extent, those lines are not joined. So they are parallel to each other. So in this type of process, so if you use automatic vectorization, because there is no joining of the lines, and then there are very lot of lines are there, and these lines do manually, it takes a lot of time. But if you do it in a automatic one, it is very fast. Only thing is, whenever the lines are there, if they are broken in between while creating the layer, and probably it will also create a similar digital line on the computer. So there you may also find the breaks. But otherwise, if the smoothly drawn and then this thing, so automatically it does very fast. Another is, suppose there is a file here, so you can say water supply lines or something. So then if you wanted to vectorize this, you can do automatic, but the things are, so many lines are joining it in between. So it will be best done if you do it in a semi-automatic method. So that means you start some line, it will start and come here. It will wait for instruction whether to go down or go straight. If you say that go straight, so automatically this line is created and it will stop at the next junction. It will also ask for the instructions. Once you give the instruction, it will follow again the line. So like this is called a semi-automatic method of digitizing techniques. The third is we have a complex document like a topographic map. All the things are there inside. So it is very difficult to extract each one using a automatic vectorization, because there are so many things overlaid one over the other, and then the process involved to rectify that, it will be very huge task. So and then it is not also what I say. No, it will take a lot of time, then you vectorize and start correcting it. And then finally you will create some more errors. So it is always better that way. Once you scan it and then do manual digitization, each feature wise. So that becomes easier and then convenient. So that will be the best process in case of complex maps. So, but if you have different, otherwise earlier days in each organization there used to be one cartographer. So the cartographer job is to extract the information from the different maps, or if it is a topographic map, they will be asked to extract what is the road network. So then you have to put a tracing paper on that and trace it and then make another map. So that if you create a themes, each theme separately, so that each theme layer you can bring it, do it, scan it and then vectorize it. It's very fast. But if you don't have cartographer, if he is then if you are not having a map which is having a only one theme, so it is difficult to that vectorize topographic maps. But if you extract some information, create a layer and a faster mode and then scan it, the vectorization is very fast. But if it is having a multiple information, then it will be manual digitization is the best option. This is semi-automatic digitization in case of the second, and third is automatic vectorization. So then cleaning process are involved is, suppose if you have two polygons and then there is a sliver in between that, so that elimination is there. Erase duplicates or sliver lines, and then we have the lines are there where the unnecessary information is also there. So erase those objects, erase that additional nodes in between that. So there are two lines are crossing, but it requires a junction for that. And then here is you have a polygon 1, 2 and 2, but why a line between again 2, what is that? Feature of 2, which may be a forest or something. So that line can be eliminated and then further edited. So here before clean up there is a undershoot. So then you remove the after cleanup, that undershoot is removed, and then what I say, node is created, and then 4 lines are coming here. But here after removal, all joining to one point, only one node is required. This is again overshoot, and then overshoot is removed, and then many of point nodes are created that you can remove it. Dissolve nodes into vector vertices. So this is the cleaning process what is involved in this. And then sometimes what happens is you create layers, maybe same framework, same projection system, but they are done by different people. So you can combine together, and then all three data sets can be combined to make it a uniform data set. So overall steps, what we have done is we scan the map, take care of that dots per inch what I mentioned. We georeference the scanned image. Before digitization, do the following: create the attributes to be associated, define snap tolerance, define tunnel tolerance in case of stream mode, digitize only at the middle, zoom and digitize, and then you have further. If somebody created two different places, so how to bring them together, seamless mosaicing, and then cut or bringing to the common projection. So this is not data analysis and output is not part of this lecture. Those things further will come up. So this is basically inputting and editing the map, creating the final layer. So there are different questions are there. I think you just read that and then try to answer yourself. So with this, I come to the conclusion of my lecture.